Okay, so I will be presenting today instead of Dr. Ashley Joshi and Joey Wong. They weren't able to attend today, so I will be presenting, but I also worked on this project collaborating with them. So my project is precision glioma grading using voting-based feature selection and ensemble machine learning with clinical and molecular data. So, as a quick introduction, each year, 80,000 people in the United States, they're diagnosed with these primary brain tumors, and around a fourth of them, which is 20,000, are gliomas. The thing about these gliomas is that they compromise of low-grade tumors and aggressive high-grade malignant tumors. Um, Short term for GBM, glioblastoma. And these gliomas, they represent the most common malignant primary tumors of the brain. So they're around 50% of these malignant tumors and 15% of all brain tumors. And the prognosis between these two groups, they vary widely because between very high-grade tumors, they have a 5-year, up to 5-year survival rate with a 5%, while median survival of 12 months and low-grade tumors have 5-year survivals where it's around 50 to 95%. And you can survive a medium survival of about 16 years, which is a big difference between these two. So it's really life or death here, and that's what is so important about classifying these gliomas. And in 2021, it's the World Health Organization. They released this revised classification of gliomas, and they based it on histology and molecular features. So these molecular information has greatly enhanced these precision diagnosis and facilitated treatment decisions and assessing prognosis and developing new like targeted therapy therapies, treatments, cures for these gliomas. However, as these molecular profiling techniques advanced and further develop, these molecular mutation landscape data for these gliomas continue to expand and expand. So the amount of testing is growing, and it's more necessary for people to get these tests for the growing number of new mutations. Now it's at least 20, maybe around 23, 24. Um, so these molecular testing, they're very expensive and they impose a massive burden on costs and resources. The cost of one individual test or assay is the IDH mutation test, one of the most important factors in identifying these gliomas. It ranges from downwards of $400 to upwards of a few thousands of dollars. Um, so identifying the smallest set of mutations can capture the same information regarding diagnosis, prognosis, and different therapeutic options without compromising accuracy. And this could substantially reduce the healthcare cost and improve equity and access to precision medicine. These glioma grading through these targeted molecular profile would also allow more focused analysis of different molecular alternations for future and depth analysis and development of targeted mutation specific therapies. So the objective of this research and this project was to identify the optimal smallest subset of mutation genes and clinical features for the glioma grading process while using a voting-based feature selection approach combined with the ensemble machine learning method without compromising predictive accuracy. So we want to reduce the amount of features needed and amount of features seen without really decreasing the accuracy because the accuracy very much matters here. So we want to keep a high accuracy and also be save some money, save some costs and time. So what we hypothesized was that first for the feature selection is that the voting-based feature selection method yields higher feature efficiency and classification accuracy compared to the lasso-based feature selection method for glioma grading. And my second hypothesis was that for the model performance is that ensemble machine learning models will achieve superior accuracy than individual-based machine learning classifiers, which means that these ensemble methods that use multiple different combinations of these base models will achieve a higher accuracy than just an individual base model. So this is a quick flow chart about my methodology. As you can see, we have the data collection, the different methods, and then we go into two different ones between lasso and voting based. With the lasso method, we have just a base machine learning model, so it's individual ones, while with the voting base, we first through three different methods and then rank the top 10 features. So it's really what shows what's most important in classifying these and how they could determine between low grade and high grade and how you can tell the difference. And then we rank the base classifier, so from top six, and with those top six, we combine them and then do different ensemble learning methods and find different combinations for the highest accuracy while getting the lowest features. So with these data collection and pre-processing, the data set for this study was obtained from UC Irvine. For example, this is the TCGA data set right here. So this data set comprised both molecular characteristics, which includes IDH mutation status, other things which involve genes, different molecular characteristics, and also clinical variables. So it can be patient age, sex, tumor grade, and these 23 categorical features and one numerical feature, which is the HI diagnosis, because the age will be a numerical feature since it just says how old the patient is, with addition to the target variable of the grade, which is low grade or high grade. So this data set was assessed for missing values, sorry. Prior to this model development, these continuous variables were scaled using z-score normalization, and also categorical variables were encoded. So this data set, which was around 305, I believe, was split into training between an 80-20 split. So 80% of these samples were split into training, while 20% was used for testing the model. So for the feature selection strategy, to address the high dimensionality of these glioma data sets, the voting-based feature selection framework was implemented, and the framework had three major categories of feature selection models. In the flowchart before, if you saw it, it was filter methods, wrapper methods, and embedded methods. So with the filter method, it's chi-squared scores, the weight of evidence, um, mutual information reply to the rank features based on the p-value, information values, and different scores. For the wrapper method, it was recursive feature elimination with cross-validation, ranked the most important features, so as a top 10 I said before. And then the embedded methods had lasso regression, random forest, and light GBM. And these really identified which features and how were the most important with the different scores. So after this, the top 10 features from the results of each feature selection method were based on their respective importance scores, and the rankings were extracted. So only those features that have an RFE rank of 1 and appear in the top 10 of at least 3 of these 6 methods were selected for further analysis. So this really shows how these different features were very like cherry picked, and they were made sure to have a good importance to the project and show how well they contribute to whether classifying if it's low grade or high grade. So these features have the features that have an RFE rank of 1 and appear in the top 10 of at least 3 were selected for further analysis. So using these classifiers, and with these classifiers, new training and testing data sets containing only the selected features, which is the top 10, were created. And these selected features were trained and tested using these following classifiers, which is a linear models, which includes logistic regression, SGD, SVM, neighbors based were KNN, ensemble methods were AdaBoost and random forest, and then these discriminant analysis were LDA and QDA. So with this, the evaluation and validation, the model performance was evaluated using a 5-fold cross-validation to preserve class balance and across the different folds. The following metrics were used. So it's accuracy, precision, recall or sensitivity, F1 score, and receiver operating characteristics, and the area under curve. So the accuracy was just the proportion of the correct prediction and how close it was to the true value. Precision was that the fraction of these predicted positives that were actually positive of a measurement. And then recall was proportion of the actual positives that are correctly identified as true positives. F1 score being the harmonic mean of precision and recall, providing a balance measure, and then RC AUC, which is the receiving operating heuristic area under curve, and measures the model's ability to distinguish between these classes. So out of these 8 models, 6 models with the highest accuracies were chosen to create these ensemble combinations. So with these 8 base models, we got the top 6 after we ranked them for accuracy for the base models. And then we used those to create the ensemble methods. And around a total of 57 unique model combinations were generated from the 6 base classifiers. And then each combination containing at least 2 classifiers or more. So for each combination, voting classifier or stacking classifier ensemble models were created. So that's around 171 different ensemble models, multiplying it with the 58. So it creates 171 ensemble models. We had hard voting, soft voting, and stacking approaches were implemented. And these trained ensemble models were evaluated using this 5-fold cross-validation with these metrics with accuracy, precision, recall, F1 score, ROC, AUC, and they were all calculated. So these top 10 performing ensemble models were based on accuracy that were identified, and then the other evaluation metrics were noted as well. So with these, okay, after I did this, I did the hyperparameter tuning strategy. So to improve this performance, grid search CV and randomized search CV, they were used for these hyperparameter optimization. These optimized the base models, and then they were used in these ensemble combinations, and they were reevaluated with, as before, the 5-fold cross-validation, same metrics, and had the same training for the ensemble. With the lasso feature selection, it was implemented using 5-fold cross-validation, and these machine learning classifiers were trained using the lasso selected features, and their performance was also evaluated using just the standard metrics, including accuracy. So for my results, these are the top 10 features for each feature selection method as I ranked them. Here it shows how many times each feature got the first rank, so how if it had the highest score or whatnot. It shows like here you can see that IDH1 and P10, they were really the standout ones. IDH1 also was in the top 10 of every single one, along with being first for 6 of them. So it shows how important this one is, how this feature really stands above the rest compared to PIK3R1. Like, it shows really the importance between these two. As well is that these features had a rank of 1 and appeared in the top 10. So with these 8 different classifiers, independently, SVM had the highest base classifier. So as an individual classifier, it had a 87.3% accuracy, with Lightroom being the second highest with 87.2. So these show the base classifiers and the accuracy for each base classifier. It shows how it's not ranked in order, but SVM here has a 87.3, second being logistic regression, and then therefore. So these voting-based feature selection methods, they use the different accuracy, they provide a better accuracy with the fewer features compared to lasso-based. Okay, here it shows that there's a total of 57 unique ensemble combinations were generated from these 6 base classifiers. So with each combination containing at least 2 classifiers. So it shows us all the combinations between these. These are also the base classifiers, and then these are each feature for the type of selection method. So again, 171 total configurations using the 3 different classifiers, the hard voting, soft voting, stacking. All of these models were trained with 5-fold cross-validation, with also standard metrics. And then the top ensemble methods achieved the high accuracies. And the ensemble methods, preferably the highest accuracy ones, focusing into logistic regression with SVM, with SGG, with KNN, along with soft voting, and then logistic regression plus AdaBoost plus SVM plus SGD, soft voting, and then AdaBoost plus SVM, SGD, KNN, and soft voting. So these showed an accuracy of 87.9. Like for example, this shows all the different combinations we did. This shows the results for these accuracies. So it shows how it's with the Ensemble learning, it's stacked from accuracy. We have accuracy upwards of 87.9. And these are also the other metrics. This is just more data tables. It shows the different accuracies, ensemble methods, and then it ranks the top 10 ensemble methods. This is a graph and it just compares the model accuracy with the number of features. So as you can see here, that ensemble voting and two-ensemble voting really stood out on the rest with these different features, but the number of features were a bit increased, but also you have to have a high accuracy, so it matters. So the goal of this study was to identify the smallest set of mutations and clinical features that could deliver a precise and accurate glioma grading. From these features, we reduced it from 23 to only 8 features compared to 14 selected by the lasso method. So it significantly outperformed the lasso in this feature efficiency while maintaining the same high predictive accuracy. So the ensemble of these multiple Bayes classifiers achieved high accuracies and confirmed that these different models, SVM, SGD, and logistic regression, they capture these data patterns and they just generalize better. So these ensemble methods, they have less errors, higher accuracies, and is more efficient. So it shows how the first comprehensive integration of these extensive voting-based feature selection framework, and it combines these different 8 feature selection methods with the ensemble of 6 machine learning classifiers. Um, so a related study was by the National Institute of Health. It combined 4 different selection methods, and with the same data set, they only reduced it from 23 to 15 compared to my 8, and they had an accuracy of 87.6%, while mine was 88.2%. So the application of this with future research is that it could substantially decrease healthcare costs since it reduces the amount of testing needed and shows that it has equitable care for these patients. So if people are in financial need and they need lower costs, this is the way to go as it can reduce it from almost 67%. It's a big decrease for the people. So it shows that an application that pinpointing these molecular determinants, such as these different genes, would have a more focused in-depth analysis. And then for future research, we can explore more feature selection methods. I already have some in mind, and then more novel-based classifiers. And overall, like the study, it just shows a different framework for precision glioma grading, and then it balances accuracy and also efficiency. I know I'm running short on time. This just shows that it just has a accuracy of 88%, reduces the feature about 65%. It shows that how the purpose of this project was to really have a purpose of decreasing these healthcare costs and making sure that most people can get this. I know healthcare is very expensive, but a lot of people that are in need, they need lower healthcare costs, lower clinical costs, and this is the way to go. So yeah.